we are ending our chapter 3 with 310, which is our last section on, it says theorems about differentiable functions. There's one that we're covering, and that is the second of our existence theorems. You might remember the IVT. I hope you remember the IVT. That was the one where we said if your function's continuous, then if you've got these two values a and b, and it's a continuous function, if f of a is 2 and f of b is 12, then there has to be some c value in between a and b where f of c equals 7, right? That means that all of those y values are accompanied by an x. So this is another existence theorem. This deals with derivatives. So this is now our MVT. And your MVT tells you if you have a function that's continuous over a closed interval AB and differentiable over the open interval AB, that just means you can take the derivative at any point except at the endpoints, then there has to be some C in between A and B where f prime of C equals f of b minus f of a over b minus a. What in the world? This is just another way of saying that there has to be a C value where the average rate of change, that's the secant line that joins A to B, equals the instantaneous rate of change. That's the tangent line. There's going to be some C in that interval where if I find the slope of the line that joins points A and B, then there will be a tangent line within that interval that has the same numerical value. So there's going to be some value where the average rate of change equals the instantaneous rate of change. I'll do a short example. So if we were given that this is a position graph, and we wanted to find over this closed interval from 3 to 5, we wanted to find the average velocity that this person was traveling, the average velocity. Well, we would take our distance equals rate times time. So we would take that ratio of distance over time to get our velocity. And that would look like this. My y's, the changes in my y's over the change in x. So 180 minus 20 over 5 minus 3, which then simplifies to 160 over 2, which is 80. Oh, and let's say this is in miles. So that means that that average velocity was 80 miles an hour. Would it make sense to you then, if my average velocity was 80 miles an hour, at some point I had to have been driving at a speed of 80 miles an hour? Even if I was just doing cruise control, 80 miles an hour, right? That's going to give me 8. Or if my speed fluctuated, if my average speed, if my average velocity was 80 miles an hour, at some point within that interval, I was driving 80 miles an hour, right? So maybe it was like right here. So that's what we're getting at with it. It's kind of an intuitive idea, right? That your average rate of change over some closed interval will equal the instantaneous rate of change at some value. We don't know where, but at some value, average will equal instantaneous, provided that your function is continuous over that closed interval and differentiable over the open interval. So let's see this in action in a couple of examples.
Here's a visual where they're showing you that average rate of change over A and B, boom, right there. That's where your C, that derivative, that instantaneous rate of change is the same. Those two lines would be parallel right at that point.
So in Delta Math, we've got these MVT questions. So they gave us this function and they graphed it below. So we got to do a little plotting here. So we're going to plot over this closed interval from x is negative 6 to negative 3. So we're going to click on the negative 6 point, and we're going to go to negative 3. And it looks like it's negative 6, negative 5, negative 3. Oh, negative 3 something. So we're going to go to our graphing calculators and figure out what that is. So it might be a little out of focus, but I'm hoping you can see I plotted that in my, or I put that in my y equals, my y1. And then the next thing is I just typed in y2 minus y1 over, x2 minus x1. And remember to get to the y, all of the y equals, it is alpha trace. And so I don't even care what those y values are. I just want my calculator to tell me what they are. And it told me that it was 4. So now we're going to go and figure out, because that's our average rate of change, where's our instantaneous rate of change also equal to 4? So here's the question that we're asking. Where is f prime of x going to equal 4? So we're going to work this out. Got 14x plus 4. So we want to figure, when is this? I have to, maybe this isn't a factoring. Oh, no, that's nice. Those two cancel out. We've got 3x squared plus 14x. No constant, so this is GCF. Oh, I cannot pull out of 3. I can pull out an x. And we've got 3x plus 14. Then ZPP. So either x equals 0 or 3x plus 14 equals 0. So x is 0, that's my answer. 3x equals negative 14. That happens when x is negative 14 thirds. So we're going to plug this into Delta Math. Here we are. There was 0 and negative 14 thirds. And this asked for values in this closed interval. So 0 is a moot point. So we cross our fingers for negative 14 thirds. It sounds so wrong. It's going to be so right. Awesome. Good. And we're done.